Hey guys, this is David Wong, and I've been working on this project called noname for a bit. And basically, this noname project is a DSL or language, or program language, to that looks kind of like Rust, to write this kind of zero knowledge circuits or zero knowledge apps where you can create a proof that some logic was run correctly, um, and some of the inputs are private, some of the inputs are public, and so you can create a proof and you can verify it and all of that. This all works based on kimchi. I'll post a link to noname, the noname repo. I guess it's here in the description of this video, but you can get it here. It's really it's a work in progress. I'm kind of like playing around, so not for production use, but I think there's a good educational opportunity in kind of showcasing this work, and this is why I'm making this video. So it's based on the kimchi proof system that we use at O1 Labs for the Mina cryptocurrency, and it's basically building on top of that. And so I can show you some of the examples that I wrote in this video, and kind of show you the outputs to kind of show you how circuits are built for the kimchi proof system. I think that's what you can get from that video. So if you want to play along, the first thing you can do is go and check that repository, and you'll see something called data. I guess I should really change that to something called examples. I think that would be better. And then you can just run, for example, the command that's written here in your terminal, and that should basically compile this example here with these inputs in debug mode, and you'll get this. You'll get a bunch like very verbose outputs, and it will basically compile this example, which I'm going to show you, and create a proof for it using these inputs that I'm passing here, which are passed using JSON, and then it will verify the proof. Just to make sure that everything works. It's sort of like a test, and the debug here is to show you some information which you'll see is useful. Okay, so let's open that example. I guess example. And sorry, I don't have syntax highlighting, but basically you can see it really looks like Rust. You're like importing modules or libraries using that use keyword. You have a main function. You have a field type because we work in a field, and the field is some field I'm not going to talk about. Probably I should document that somewhere. So it's really the numbers from 0 to like a large number. And here you have arrays, so you have these kind of like primitive types, and there's like a pub keywords here to just say that this argument is actually public. So the verifier will need this public this argument to like verify the proof, but this doesn't have the pub keyword, so you won't need this to verify the proof. So this is really a private input. Only the prover who runs that main function will know what's in there. And the circuit is pretty simple. It just takes a private input, which is an array of two field elements, and just add them and make sure that the result is equal to 2. And then it uses the crypto module to run a hash function called Poseidon on the private input, and make sure that the digest that you're getting is equal to the public input passed to the function. So Poseidon is a bit complicated, so I don't want to really talk about that now. I'm going to take a more simple example. I'm going to take the arithmetic example, which is just adding the private input and the public input and making sure it's equal to 2. And that's the assert equals built-in function, and you'll see how it's created. So okay, so I'll do cargo run path data arithmetic, but no. And I think if I try it like that, it's gonna tell me that something is wrong because I'm not passing the public input or the private input. So let's try. Yeah, you need to pass the following argument, private input. Like it's missing the private input. So the way it works, again, you're using JSON, so you do private inputs, and then you put a JSON string, and JSON string just has the name of the argument. So here it's private input, but we can call that for example B. We can call the public input A. Maybe that's easier. So here private input is B, and it's going to be equal to an array. It's kind of ugly, but basically arguments are list of field elements. But here it's a single field element here, so we only have a list of length 1, and so we're gonna say it's equal to 1, and we're gonna pass a public input. Oops, I'm gonna close that, which is equal to A, and which is equal to 1 as well. All right, let's see if that works. Private inputs. Okay, public inputs, private inputs. Really nice. Oh, maybe I didn't save that file. Okay, I saved it. Okay, cool. It works. Proof is created and everything. You can see the weakness. I'll talk about that later. And you can see some debug information, which I'm going to go through now. Actually, just want to show you what if I didn't have the debug. If I didn't have the debug, it would just print some assembly language, which is basically what Kimchi needs. So Kimchi needs so that's the version of the system. It's not really important, but Kimchi needs a list of gates, and the double generic gate is also called the generic gates. I guess my Google Home got activated. Anyway, the generic gate is just a gate that allows you to do A plus B equals something, or A times B equals something, and things like that. And so I'll explain exactly how it works. But basically, you can build circuits using these gates, and the generic gate is the most basic gate that you can use to build circuits, because you can use addition and multiplication to build everything. And in Kimchi we have what we call custom gates, which are very specialized gates, like you can find in CPUs, for example, to like do hashing or accelerate some operations that are pretty common. The other thing that you need is a wiring, and basically gates have inputs and outputs, and sometimes you want to use the output of a gate as the input of another gate. So for example, you want to say gate 1 is going to be A plus B equals C, and then you have gate 2, which is D plus E equals F, or equals, let's say, equals 2. Maybe this is your circuit, but you also want this D to be equal to C. So you want this value, this output here of that first gate to be the left input of the gate number 2. And so this is basically the wiring that's happening here, and I'll explain exactly why these things here gives you these circuits, and so you'll understand how it works. And yeah, proof created, proof verified, everything works. Cool. So let's use the debug now, and let's analyze the outputs. And okay, so you can see in the output we have the witness. Again, I'm not gonna talk about that now. The wiring and the gates. So let's look at the gates first. The gate number 1, it tells us so it's the double generic with is tweaked with the value 1. More about that later. And it's created from that line in the code, okay, from the first line, and it's specifically from that argument, the argument A. And it says that this gate was created to add the public inputs. So public inputs in Plonk, so in Kimchi, which is a Plonkish protocol, ignore that if you don't know what I'm saying, is the honor proof system where you have to encode your public inputs as gates in the beginning of your list of gates, in the beginning of your circuits. So that's what's happening here. Usually to add public gates, you just want to say that you just want to add that constraint here, like public value equals 0. Here is A equals 0, and later on the verifier will make sure that that it's actually A minus 3 or something like that equals 0, and they will actually instantiate what that public value needs to be. So the verifier will make sure that you run the function main with a equals to 3, and they will do that. But as the prover, what you're constructing is just this a equals 0, which is wrong, but the verifier will do something to fix it. I don't want to go too much into the details here, but basically this is what you do when you create a public input, and there's more to understand about that, but yeah, that's just how public input works. Okay, and let's leave it at that, and let's go to the next gate. And now we have adding two variables together. This b plus a here, right? The second line has prompted the creation of another generic gate. It's called double generic because we can do two generic operations in kimchi, contrary to Plonk. But I'm not going to explain that, and actually we don't use that in noname. In this framework, it's actually we're just using it as a generic gate. But again, you can ignore that if it doesn't make sense. Okay, so now I'm gonna have to explain what these numbers are. So basically, the generic gate, the way it works is that it creates the following constraints: left input times let's say C0 plus right input times C1 plus the output times C2 plus left times right input times C3 plus we're going to ignore copilot here, plus some constants equals 0. And basically these numbers here are the values of C0, C1, C2, C3, and C4. And so if we go back here, basically it means that all of the C's are 0 except for the first C0. So what we did is left input times 1 equals 0. And it's that value here. And here we have 1, 1, and minus 1. So what does it mean? It means L times 1 plus R times 1 plus O times minus 1, and everything else is 0, equals 0. And you can rewrite that as L plus R equals O, which is the left input plus the right input equals the output. This is basically how you constrain an addition. You use a generic gate with these values for the coefficients, and this is how you constrain an addition. If you wanted to do multiplication, we don't have one here. Actually, maybe I can do it. Change that here so I don't get an error. Oops. Let's add that as comments. Not yet implemented. I guess I haven't implemented the multiplication yet. So, wow, I forgot. As I said, it's really work in progress, so I cannot even show you that. But I'll tell you then, if I wanted to do a multiplication here, basically the multiplication is here. You have to do you have to set C0 to 0, C1 to 0, C2 to minus 1, because you have to negate the output if it's on the left hand side of the equation. And then the multiplication here is 1. And so you get L times R minus O equals 0, which is the same as L times R plus the output. Okay, and don't hesitate to pause the video if you want to think more about that. And the C4 here is really used as a constant, and I'll explain that because we're going to have to these two here is a constant, so it's going to use this thing, so you'll see. Okay, I'm going to comment that, so I can keep this. And let's run that again to get the gates. So we were here, so we basically are creating these gates to say, yeah, we're constraining this addition, b plus a equals c. And in here I'll call that x, because this is what's happening here, right? Maybe let's get 1, get 0 as here. So that's how you do an addition. What should I say? I can mention also that here b plus a are almost unconstrained. B is unconstrained so far. This is the first time we're seeing b. It's going to be used in these gates. But the a here, we have to make sure that it's the same as the public input from that gate. and you'll see that in the wiring. We'll make sure that what's in the get 0 is actually going to the get 1. So maybe let me add that here. We will need get 0 and get 0 the left input, right? Left input to be wired to get 1, and I'm not sure here, it's probably in the right input, so we'll say this. And the left input is basically the ZRF argument, and the right input is basically the let's write it like this, the first argument. Now we have the assert equal, but it's not creating this get number 2 because of the assert equal. It's actually creating it for the constant here. We need to make sure that we can assert that x is equal to like a constant, so we have to hard code that in the circuit. And this is where we use that C4 here as -2. So basically it's going to say L times 1, right? C0 is set to 1, and then everything is set to 0 except the constant there plus -2, so -2 equals 0, right? So it's left -2 equals 0, which is the same as saying that L equals 2. And of course we're always mod some outer field, but I'm gonna ignore that. Cool. So I'm constraining the get 2, the first argument of get 2 to be equal to 2, basically. So the prover can put any value there, like in a get 2, the first argument of get 2, they can put any value, but if they don't put the value 2, then that get will prevent the proof from being created. It won't be able to verify. And you can see here, encoding the constant. Okay, now let's look at get 3, and this is the assert equal, and it's basically implementing the assert equal by constraining that here constant, so it's probably 2, minus whatever is here is equal to 0. There are other ways, optimal ways to implement that actually, but I'm not going to talk about that. But if you know, if you're thinking, oh my god, that's not a very efficient way to implement the assert equal here, you're right. And if you want to submit a PR to change that, you're welcome to try. But anyway, this is how we check equality, and you can guess what's happening here. It's doing left times 1 plus right times -1 and plus a bunch of zeros equals 0, because all of the other C's are zeros, so it's the same as saying left equals right. And again, that gate here, so gate number 3, let's write that here. We will need get the first argument of gate 2, which is that constant, right, that we hard code in the circuit, to be wired to gate number 3, and I think the constant is on the left here, so we're gonna say the first argument here. So we need to make sure that this gate that implements the assert equal is using as an input the value that was in another gate 2. That's the wiring. Cool. So I think that's all, right? So it's only 4 gates starting from 0 to implement basically a public input, an addition, the encoding of a constant, and the assert equal. And we could actually make it shorter, as I mentioned, but I'm not going to explain how. The wiring is what do we say? We said here the A in that addition in gate 1 will need to be coming from the encoding of that public input, which is in gate 0, right? So let's see. Indeed, we're trying to wire the public input here to that addition, to what the gate using that addition. And so, as I said, it's gate 0, emplacement 0, or register 0, or input 0. I don't know how you want to call it. So this is it. Gate 0, value 0, is linked to gate 1, value 1, which is what I said previously. so the right input of that gate. Next, I said we need to like make sure that the encoded value 2, the constant, which is in gate 2, is, oh, actually here it's x, right? It's something I missed. Actually, the x, the result of this addition, which is in gate 1, so gate 1, and I guess the output is in position 2, starting from 0. It also needs to be linked to that that assert equal, which is in gate 3, and the x is actually in the right input here, which is correct, right? Because I said that the constant here was linked to the left input of gate 3. So here you have it be you have the x, the variable, not the constant, wired to the right input. Okay, finally the constant here, which is in gate number 2 and placement 0, is wired to our assert equal, gate number 3, left input. And that's it. This is all the wiring we could have done. Okay, I'll mention how we could have implemented it better, actually. Maybe that's interesting. We could have just wired the value x here, which is in the output of gate number 1. We could have wired the output of gate number 1 to be the constant 2, so the left input of gate number 2. We could have just wired that, and so the prover couldn't have used a different x, otherwise that wire wouldn't, with the number 2, wouldn't have worked. Okay, hopefully that makes sense. Of course, that video is probably not making a lot of sense if you don't have some basis, or if you haven't watched the Plonk series that I have, which I guess I'll link in the description as well. And finally, there's some witness here. It tells you exactly the values that it added to all of the rows that we created. So we have 4 gates, right? Gate 0, gate 1, gate 2, gate 3. In the first gate, if you remember, it was for the public input here, and the public input we used was 1, so it's on the left position. There's 15 position, by the way, in Kimchi, but we only ever used, for the generic gate, we only used the first 3, I guess. We actually, didn't we use 2 as the constants? Is there a bug somewhere? So 2, we use that -2 here. Oh yeah, no, there's no bug. So these are this -2 here is the coefficient, right? So the witness has nothing to do with the coefficients. It's what you put as the prover. It's kind of like your execution trace, like the values of the variables at that point in time when you were running the circuit. So use 1 as a public input. Gate number 1 was the addition here. So you used 1 here, which is the private input B, and you used 1 here, which is the public inputs, which is 1 also. And these two are wired together. This 1 and 1 are wired together, if you remember correctly, and the output is 2. Right, the output is 2. Remember, it's like 1 plus 1 plus -1 times 2 equals 0. Then we encode we hardcode the value 2 in the circuit, so it's the left input of the gates. And finally, we say left minus right equals 0. And if I remember correctly, this is wired to this, and this here, the right input is wired to the output of the addition gate. And that's how you can read the witness. And yeah, hopefully that makes sense. I'm gonna leave it there at that. I guess I could show you other. So basically, if you look at the data folder, there are other examples. There is like how to use an array, and you also have the assembly, how to use a booleans, how to use equalities, how to use for loops, how to use, there's a mutable keyword like in Rust also, how to use Poseidon, which is the hash function, how to use public outputs. You can also return a value with your function. And I guess we don't have custom types yet, so you cannot write a custom type like that. I don't believe this will compile. If I remember correctly, it doesn't work yet. and I have a Sudoku example that doesn't compile yet. But I believe this is what I want methods to look like implemented on types. So this is kind of inspired by Go instead of using the Rust way. But I haven't actually implemented that yet. So if you have any suggestions or feedback, you can let me know. And maybe if there is enough interest, I can make other videos to explain how other programs and are related to their circuits. Maybe I can do exactly the same I did here for the arithmetic example, but with other programs, if that's interesting to you. Anyway, yeah, I guess I'll stop now, and yeah, feel free to toy around. A lot of things are not implemented, so if you kind of want to learn about circuits, you're welcome to also contribute. And yeah, hope you enjoyed.